Okay, yeah. So your mark will almost reflect your performance in class. So how much you put in, then um, what you achieve. Like what I said last time, word done, word done. Okay, make sure your word done is correct. All right, so let's start. So 开始了. Where did we stop last time? We stopped at the fundamental theorem of line integral. Of line integral. So how should we think about this fundamental theorem of line integral? What's the analog we used last time? Anyone still remember? What's the analog we use? We relate this to what have you learned before? Also fundamental theorem. Fundamental theorem of what? Calculus. Okay, so from fundamental theorem of calculus, what do you learn? FTC. Integrating what? What's fundamental theorem of calculus? Huh? Fx dx equals to what? Fa. Fa minus Fa. Oh, capital F. Okay, so what's the relation between capital F and small f? Capital F, what's the relation between capital F and small f? If what? Bf prime equals to small f. Okay, so meaning the small f is the derivative of capital F. In other words, the capital F is the anti-derivative of small f. Okay, then you can use this. This is what you have been doing always, right? When you compute the definite integral. But for fundamental theorem of line integral, what do we get? From here, we can obtain what? The integral of a curve. Okay, line integral, right? Okay, we do a general line. Okay, and then integrate over what? Over a gradient function now. Okay, sorry. Cannot see. Oh, sorry. 诶，为什么？哦，我没有办法放大，sorry. Okay, so we integrate over a gradient function. Then meaning what? What's the antiderivative of this gradient? It is just f itself. Okay. And then the difference between 2 points. What's the 2 point here in this case? What do you think? What are the 2 points here? F evaluate at where? AB. So what's the AB now? Where do you get the A? Where do you get the B from? Time. Time for what? Time for what? Sorry? RT. RT describing what? RT describing what? RT is what? Parameterized curve, right? So where is the curve here? Where got curve? Where is the curve? C, right? Okay. So we parameterize our curve C using RT, and then this curve is definite. So there's a time there. Time going from where to where? A to B. So how does A and B play a role here? F evaluate at what point? Huh? At B, yeah. RB? Why not B? Not B? 为什么不是 B？为什么不是这样？它不是 simple 不是 single variable， 谁不是 single variable？ F, okay? F here usually is what function? Function, multivariable, right? Usually here is a function of, let me start here. Here is usually a function of 2 or 3 variables here. Okay, that's why we have this gradient, right? How do we define this gradient vector? Gradient vector, still remember or not? Del F. So what is delta F here? You get del F over del X, del F over del Y, and so on. Okay. So this is called what? The gradient of F. Okay. Right. So how to turn B and A into a point? You just check your curve at the time B and time A. Okay. Not that RB is the ending point of your curve, and then RN is your starting point of your curve. Then this is similar to the fundamental theorem of calculus already, right? You take the large, can I say large number? Cannot say, because maybe you take negative. Okay, you take the upper limit, okay, you evaluate at the upper limit minus the lower limit here. Okay, if the curve is the same. So you should imagine this curve. Okay, whenever we talk about this curve, right, you should imagine you have a curve like this. Okay, this is the curve C. And then it start at RA and then stop at RB, for example. Okay, there's the orientation. Okay, you want to do integration along this curve. Okay, like, okay, in FTC, what's the curve you integrate over? It is just a straight line, okay, from A to B. Okay or not? So this is the difference between calculus 1 and calculus 2. In calculus 2, the line you integrate over can be curved, no longer straight anymore. Okay, make sense? Okay, you want to Okay, so let's do one example here. Let's compute this integral, line integral here. So I want to compute this FR, which is minus C times R over the norm of R cubed. Anyone still remember this vector field or not? 有谁记得吗？不记得。有一个 R cube 的，很特别的这个有一个 R cube。It's the first example we've seen the gravitational force. Okay, gravitational force. Okay, 我拉回去给你看。Maybe we don't write in R form, we write in X, Y, Z form. See, to refresh your memory. Yeah. Is it this one? With yeah, this one. This one. Okay. And just that we combine the coefficient just now. And then you have a R over the norm of R cube. Okay. Yeah, makes sense. Okay. So this is the gravitational vector field, and you want to integrate over this piecewise smooth curve here. Okay, you have a piecewise smooth curve from, let's say, a point 3, 4, 1, 2 to 2, 2, 0. Okay, where's 3, 4, 1, 2, 2, 2, 0? So maybe 3 is here, 2, 2, 2 is here. Okay, so we're backward here. But I didn't tell you. I didn't tell you what is the smooth curves, the parametrization of the smooth curve. Okay, I didn't tell you. Okay, I didn't tell you about the parametrization of the smooth curve. Right? So how to do this? Any idea? So usually what we do was we parameterize RT, right? The curve in RT, and then RT is going from A to B. So what do we do? Do you still remember how to compute this word done here? This is a force time distance, integral over force time distance is a word done. Is a continuous, is a continuous version of a word done. So still remember what we do? We change the r variable to t variable, okay, and then we compute what? The integral of the dot product between fr and what? 还记得吗 And what? dx dt dt dy dt, for example, dz dt, and then time dt here. So we need to replace f with rt also. Okay. 对吗？还记得吗？ OK， 应该忘记了。回来看一下这个。This one， 看一下我们讨论过的 example。Yeah, I think it's this one. Okay, so how do you compute it? So you have a vector field. Okay, you want to compute integral of vector field dot dr. What do? You can compute f1 dot dx and f2 dot dx. But what does it mean? You just parameterize, okay, in your x direction and in your y direction. Okay, then sum that all your integral will be in terms of t. It's the same. It's the same as what I did here. It's the same. Okay, it's the same as what I did because what do you do here? Why are you dotting here actually? So you should be dotting f1 of rt, f2 of rt, and f3 of rt with these dx, dt, dy, dt, and then dz over dt here. Okay, and then if you compute the dot product, how many terms do you have? How many terms? The summation of 3 terms, right? Okay, you have summation of 3 terms. f1 dot rt with dx, dt, dt, and then plus f2 rt dx dt dot dt plus f3 rt dz dt dot dt. Okay, so. But what are these? 这些是什么 ？OK， 可能你对这个 ds dt not familiar right？ 可能我把它变成这个，你会比较 familiar 一点？有没有印象 ？What are these? These are the integral with respect to x, y, and z. OK， 有印象吗 ？OK， 如果没有印象，我们再翻一翻。Where is it? Yeah, this one. I'm talking about this. 有印象吗 ？Integral function of two variables with respect to dx. What is it? If you parameterize your curve, you will get x prime. You will integrate over t, but with an extra factor x prime t. Okay? Yeah. Okay. So the creation of this definition exactly is for us to compute word done. OK， 这个为什么我们 define 这个，就是我们的 word done 会出现的 integral。OK，but but 什么 ？But this question doesn't tell you what curve is this， 它没有告诉你这个 curve 的 RT 是什么，怎么做呢？还做得到吗？没有告诉你啊？Sorry，问题是 你讲什么？没有听到。分解成两个 vector 什么意思哦？这样分解。哦，you mean 这样子啊？and then 拿一个这个 path，可是 I mean 为什么我一定要拿这个直的 path？我不一定是 straight line 啊，这题目没有说是 straight line segment，是随便的啊。OK OK，可以，等一下先，我们先解决掉这个事情先。So just now, just now Isam was like us was suggesting we should use a straight line connecting 220 and 3412 here, but you cannot do it. Why? Because the question doesn't tell you that way. It just says any piecewise move curve. Okay, you don't know how the curve move, but you know that it's a piecewise move curve only. Okay, but we're gonna use fundamental theorem of line integral here. Remember, when we use fundamental theorem of line integral, we only need to depend on the starting point and the end point. You don't need to know how the line get passed through. Okay, as long as you have what? A piecewise smooth curve here, is it? Let's check, you see? In this segment here, what you really need is a piecewise smooth curve here. Okay, although this question says that it's parameterized by some RT, but in this calculation here, doesn't involve, okay, in the proof doesn't involve the parameterization. You only need to know what is the endpoint, RB and RA. Okay, so to use this, you need to somehow know what is the capital F. Okay, so what's the capital F here? Oh, I mean, sorry. Here, it already named it as capital F, right? So you need to know the small f. So can you write? So the question is, can you? So okay. So the question is to use fundamental theorem of calculus. The question is, do you know that f capital F hat here is equal to a gradient of some small f? Okay. If this is true, then by ft LT, fundamental theorem of line integral, you will know that this integral is equals to the to what? The small f on R, let's say B minus FR A. Okay, which you know where's the endpoint, right? Where's the endpoint in your case? What's the endpoint? 2, 2, 0. And then your starting point is 3, 4, 12. Okay, but to write a vector field as a gradient of another vector field, a gradient of a scalar field. So here should be a scalar field here. Okay, this one. Okay, so let me label here. So here is a scalar field. The other side is a vector field. Okay, so to write a vector field in this way means what? What's the definition? We call this vector field as a conservative vector field. Okay, if you remember last time when we teach conservative vector field, there's one example we go through. Okay, so there's one example we go through here. So let's recall again. There's a lot of things we need to recall. Yeah, there's really only one example we've gone through. So we have shown that this gravitational force field is a conservative vector field. And then the scalar function is this C over square root of x squared plus y squared plus x squared. Okay, so this is the scalar field you need. Okay, for that question. Okay, just back. Okay, where am I? Okay, so what's this f here? So let's put. So the f is really c over square root x squared plus y squared plus z squared. Okay, so can you quickly compute for me? What's this number here? 来算一算，女生都要睡觉了。算这个，来算一下。Using the small f, what do you get? Small f, what do you get here? C times something. 啊，等一下给我们算一下，让我们温饱一下。OK，try 吗？放进去算了。OK， what's the first term you get from F2 to 0? 啊，1 over 2 times square root 2, 3, 4, 12, 1 minus 30. There you should get it. Okay, so this is one nice thing about this fundamental theorem of line integral. If you know that your vector field is a conservative vector field, then you just apply the little f, okay, the scalar field. Another name for this in physics, right? We call it what? Potential function. Okay, if you remember, potential function. Okay, where you just take the difference between these two potential function at the endpoint. Evaluate at the endpoint. Okay, any question? Okay, so this method is particularly good if you don't know what curve you are considering. Okay, but not that here, not that here. There's an extra condition here. Did you notice what the condition say? This path does not pass through the origin. Why? What do you think? 为什么不会 pass through origin? Ah, 你要从哪里想 Obviously 你要从那个 vector field 开始想哦，不然呢，对不对？它肯定跟那个 vector field 有关系。什么叫 converge to origin 呢？这个 vector field 是 converge to origin。But what's the value at the origin for this vector field? 被零除有可能咩？没有啊，不 define。OK OK yeah. It's not defined there. OK, it's not defined there. 这个就是刚才早上那个谁啊，那个子莹讨论的不是咩？Black hole Black hole 那个点那个点我不知道发生什么事情，其实 这就是物理界现在最大的谜团。Because they treat black hole as a singularity， 算不出那个东西，我不知道那个东西里面是什么。Yeah, okay. Yeah, it's undefined. It's a singularity point. Okay. Continue. Okay. Continue. I think we will do one theorem and then we break. Okay, we do one theorem, we prove it, and then we break. We'll take a break. So next, we'll learn about one very advanced concept in topology. I think you will see it again in the MA2 or if you take general topology. So a set is connected if 2 points in D can be joined by a piecewise smooth curve line entirely in D. So does this make sense or not? When we say two things are connected, we say that if there's a path that connects them. 对吗？合理吗？两个东西是连在一起，当我们有 path between 它们。Does that make sense？ 合理吗？没有啦 ，in real life 嘛 ，in real life。For example，最近那个 A3 是不是在 A3 啊，建了一条新的路啊，被人踩出来了。对啊，因为那两个点被人家天天踩出来，天天踩，天天踩，天天踩，没有办法种下去还是被踩了，那不是做路就好了，对不对？不是有个 path connect 那两个点 ，OK，yeah，OK， so now we want to decide which of these set are connected. Basically, there are 4 of them. 1, 2, 3, 4, 5. Okay, which one do you think they are connected? Huh? Let's look at one first. Connected set means what? A set is connected means if any 2 points in D, 随便哪两个都要有 path connect 2 of them. Okay, so if you randomly take 2 points in set A, can you find a path that connect them? Okay, so seems true, okay, because you can form any piecewise curve. 2 connected or not? You know which part we are considering? The one that we colored. So for part 2, is a pink colored region path connected or not? Is it true? If you randomly take 2 points, is it connected? Okay. So if I take here and here, can I connect this way or not? Cannot, right? Because we remove the black part. But are they still connected or not? Are they still connected? How? 走一圈咯 ，OK， 这边再做路封掉，你要走远一点 ，OK，still connect. C, I mean C is easier to see 啊 ，correct or not？ 这边路没有被封，更好走。Four, is it true? If you take any 2 points, they are connected. Okay. You can go around the hole. We call it hole. 有洞，有湖啊，那有湖在那边，走不过。5呢？啊 ，not connected. Why not connected? Not connected means what? Okay, 要做上关系。Okay, but mathematically says what? You need to check for every 2 points, right? Negation means what? There exists 2 points such that you cannot connect with a path. Okay, so can you find the 2 points or not that cannot be connected by a path? Lying inside the set. 啊，可以找2个点吗？找2个点给我看。你讲接不起来了。啊 ？You take a point from E1 and then take another point from E2. Then, if you form a path here, this path is not living inside the green region. Okay, so it's not the path we can consider here. But within this E1 and within E3, within E4, it is still connected. Okay, and then we will say that here we have 1, 2, 3, 4, 4 connected components here. Okay. 4 connected components. Itself, the EI itself is connected. But if you consider all of them together, they are not connected， 对吗？比如说有一只鱼在这边游，另外一只鱼在1、2那边游，它不会跳过去的嘛？它跳不过去。OK， 它游不过去了，它可能可以跳过去，但是它游不过去。OK, makes sense. Good. So here we'll say that not connected, but having 4 connected components. Okay. And then the other thing we want to define is closed. What do we mean by a curve is closed? So a curve is closed if its terminal point coincide with its initial point. So meaning whenever we talk about closed curve, it is a loop. That is just a loop. Okay. What is a curve that is not closed? Jinsen. You or maybe something like this. Okay, yeah, sure. This is not closed. Okay, because the terminal point and initial point is different. Okay. So next definition before we go into theorem. The line integral is said to be independent of path. So this is about line integral. Right? When we say that it is independent of path in a connected set, so this is what we defined just now. Every 2 points inside the set can be joined by the path if also you take any 2 points in D, the line integral has the same value for every path. It takes from A to B. Meaning what? Meaning if you have a point, so let's say we got a connected set D here, and then you have 2 points A and B, and what? I can take any path here, any path. Okay, maybe C1, C2, C3, C4. But for all these paths here, right, this line integral should compute to the same number. Okay, if it is independent of path. Okay, and 不止哦，其实这 definition 还有一个 arbitrary. It has to be true for any 2 points in AB. OK， 每一个 AB 点的不同的 C， 还有每什么？每2个不同在 D 的点也要对。You understand？ 就是比如说 I can take A2, B2 here. Also has to be true for all these points. OK， 有2次。OK， 你拿2个 AB。OK， 拿2个 point. If you consider all paths, their integral should be the same. And if you take different endpoint A2 and B2, and you consider all paths, they have to be the same. 不一定跟这个一样啊。It's not necessarily the same for. Let me think. Yeah, so it's not necessarily same with these. So let me be clear a bit. So let's say these are D, D1, D2, let's say D3, right? The integral of DI should be the same also. Okay? Okay. 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 我没有 claim 这2个是一样啊，这个可以不一样。Okay, but as long as you fix your 2 endpoint, all their line integral should be the same. And then we will say that this line integral is independent of path. 就是说 independent of path, but dependent on 什么？ It is independent of path, but dependent on what? AB. Dependent on your endpoints. 对不对？就有点像那个 fundamental line fundamental theorem of line integral， 你只要用 endpoint， 你就可以决定你的integral。Okay. Okay. How about we take a break now? We take a break first, then we can continue with theorem. Okay, let's break until 2:02. Okay, so let's go with the last hour here. So we'll introduce a few theorems to tell you what are the equivalent way to say that a vector field is conservative. Okay. So before doing that, we will introduce these two equivalent statement here. So first statement is, let's say I got a vector field. Sorry. I have a line integral on a vector field that is independent of path, so meaning just depend on endpoint. Then I can prove that this is only true if and only if the line integral over a closed path, meaning a loop, is zero. Okay? Can you think about it? I think one direction is easy. Can you think about which direction is easy? So you should think about if I have a path from A to B. Okay, how do I form a closed path at A, for example? A equal B. A equal B is just a point, right? Now I was trying to say that if I have a path from, let's say, from A to B, okay, okay, A to B, can you form a closed path or not at A? Right? If I have a bunch of paths, let's say like this, okay, let's say these are C1, C2, C3, C4, maybe give you a direction. So we have direction like that. Can you form a closed path at A? Maybe you do C1 minus C4, okay, or C1 minus C2, or C2 minus C3. Yeah. So if you change the orientation of the path, meaning you are moving from the endpoint to the starting point. So which directions is easier to prove? So I claim that left to right is easier to prove. Okay, left to right is easier to prove. Why? So let me show you. So to show left to right, what you want to show is you want to show that the line integral over all closed paths should be 0. Okay, but how do you form a closed path? So let's say you have a closed path, right? Let's call the initial and terminal point, or the ending point is A. Okay, how do you build this path here? Then how do you build this path? So you can split this curve into two parts. Okay, I don't know where is the half, but obviously I can split it into two parts, right? We just pick any other point on this loop, okay, and then I just call it B. I don't know. So this loop at A, is a path from A to B and B to A. Okay, so let's split this loop into let's say C1 and C2. So this integral will becomes what? The union of C1 and C2. Okay, but what did we show for the property for line integral? If our domain is a union of two paths, we can split, right? What's that property called? Start with A. Start with A. Is it start with A? Additivity, right? Additivity of line integral. Okay, because the intersection between these two lines is just finite points. Okay, so we can split the integral out. This is one of the linearity, or not linearity. So this is one of the property of line integral. Okay, make sense? Okay, this is the additivity of your line integral. So if you want to recall additivity. Okay, but C1 is going from A to B, and C2 is going from B to A. Okay, B to A, okay, right. Then what? We haven't used assumption yet. What does the assumption say now? What does the assumption say? Huh? Independent of path. Okay, so this line integral is independent on path, just dependent on the endpoint. Okay, so did you notice that? Did you notice that maybe we can replace the second integral as what? As the negative of C1 from B to A. Independent of path, minus C1 is also a path from B to A. So I can replace this path here. As long as my starting point and the end point is the same because it is independent on time. 所以我怎么不要选一个减 C？ 选减 C 有什么好处呢？啊 ，Do you remember how does the orientation affect the integral? You can bring out the minus sign. So once you bring out the minus sign, what did you notice here? Actually, you are taking difference of two same things. So you should get 0. And here we use the assumption here, independent. Of okay. And then last part here is the orientation on then the effect of orientation of curve on the integral. Okay, you can bring up the minus. Okay, no? Yeah. So I asked you why max is nice, right? I think max is nice is because of this. Every line you should have reasoning one. You should have reasoning. 你要有原因，可能你的原因不被理解，但是一定要有原因。我是不接受上面给我的工作来，你给我做这个做那个做那个。我如果 point out 一个原因不好了，他不听，我就是跟他斗到底了。I don't care。真的，我是这样的人，我是这样的人，我会 fight 到底的，因为我原因是对的嘛，就问你跟我反而已，然后你又没有好好讲，我是 fight 到底的。啊，你看到今天啊，你们可以用 A3 啊，我已经2个 semester 没有用 A3 了，我已经2个 semester 没有用 A3 了，就到刚刚我才重新踏进去那个班。Yeah. So we work on principle 啊 ，we work on principle。如果对的东西 must prevail one， 最后一定会成功。Okay. How about the other direction? The other direction is also not too hard actually. The other direction. The other direction also not too hard. The other direction is we want to show that FC is sorry, the line integral of f over c is independent of time. Independent. Okay, independent of half. Right. So to show this, what do we need to do? You need to show it is true for any 2AB in D, and then any part between AB. So 要选什么先？要选什么先？ You need to take any AB in D first. Okay, in D. And then you need to take also any two curves that connecting A and B. Okay. Right. So you want to show that integral over. So again, rewrite our goal. More specific, we want to show that integral over C1 of f dr is equals to the integral of C2 f dr. Okay. So now, what's your assumption? I did the assumption. Integral over a closed curve is 0. So to use that assumption, you need to build a closed curve first. Right, you need to build a closed curve first. But in this case here, you have A and B, okay, and then you have two paths, C1 and C2. Connecting A to B, to be precise, we have orientation. Can you find a closed curve here? 找得到吗？ Can you find closed curve out from these two paths here? Out. Can you build a closed curve here out of these two paths? C1 union minus C2. Okay, you change the orientation. Or you want to take C2 minus union C1. C2 union minus C1 also can. Okay, both can. So what did you know? By assumption, we know that 0 is equals to the uh, u integration of C. Okay, because C is a closed path. Okay, but what is C here? Is the union of C1 and minus C2. Again, using the additivity of integral, we can split out the integral. And using the orientation on curve, we can bring the negative out. Then this difference is equal to 0, meaning what? Integration over C1 is equal to the integration over C2. Yeah. So this implies that the integration over C1 is equal to the integration over C2. Okay. Can So basically the idea involved here is I give you path. How do you produce loop for me? And I give you loops. How do you produce path for me? That's all. Okay, and then all the other thing is just a property of line integral. Okay. Okay. So far so good. Okay. Next theorem. So now we try to link, okay, independent of path, line integral independent of path to conservative vector field. So what it says here. So if you have an F, okay, which is continuous on an open connected set. So here we got more property you need to check. So we need to have a open connected set. Previously we just have, I guess this D should be connected. Okay, previously you just need connected, but here you need an open connected set. Then the line integral is independent of path if and only if f can be written as a gradient of some scalar function. So meaning, if the independent of path property happens, if and only if this capital F here is a gradient of some scalar function. Okay, I mean one direction is easy. What do you think? Huh? Which direction is easy? There are two directions, right? So what do you think? Which direction is easy? So for this kind of if and only if statement, right, you need to build some intuition. 你要一来 if and only if 你就要猜了哪一个方向会比较简单。通常都会有一个方向比较简单。Okay, if and only if. So try and guess, huh? Right to left. Why right to left is easier? And so if you do this line integral, right? Okay. Right to left meaning you already know that you can write it as a gradient of some scalar function. Okay, but how do you compute this? Integral of a gradient function. You can use fundamental theorem of line integral. What do you get in this case? F of the endpoint minus f of the starting point. Okay. So how does this prove that the line integral doesn't independent of path indeed? Why this number doesn't change? See, in this statement here, C doesn't have to be closed path. In this statement here, it doesn't say that this path has to be closed. But what do we know about the relation between integral of closed path and independent of path? Do you remember the statement we just proven. A line integral is independent of path if and only if what? What is zero? What is zero? Huh? What is zero? What did you say? What is zero? The line integral is zero. But where did you do the line integral? On every closed path. So if you can check that this line integral is always zero and every closed path, also imply that when you do the line integral random path, it is independent on path. Okay, so if I replace this C with closed path, do you always get zero? Why? For a closed path, what is the start point and ending point? Is the same point. Okay, so we cannot check for all curve, but we can check for all closed curve C. Okay, we know that this is zero. Okay, because the starting point and the ending point should be the same endpoint. Okay, and then by previous theorem, because since we already checked on all closed paths, then this line integral on random path is also independent of. Any question? We are using what we have proven in previous statement. We are using the result now. Okay. We are using the result. OK 有问题吗？有问题吗？ Feel free to ask them. Okay, the other direction is slightly harder. Okay, the other direction you need ODE. I think we don't want to do it here. Yeah, maybe we can. I can let you see what happens. But I'm good. Huh? Yeah. I think. Did you cover? Maybe you cover some of it. So in the other direction, you need to find what the scalar function for me. The other direction is what? You need to assume that the integral is independent of path, and then you prove that it is a conservative vector field. To prove that it is a conservative vector field means what? It is a gradient of some scalar function. So you need to pick the scalar function for me. Or you need to prove it exists. Okay, in this case here, we find it for you. What is the scalar function here? Let me see. So the scalar function we find here look like this. This is my scalar function actually. So actually it's the integral. Okay, integral of your f actually. 正常嘛 antiderivative. Yeah, 就是 antiderivative, but this is a two-dimensional version. 最近这个几年到这了，每次出这种东西。Okay, but how do you do this? Actually, you need to use this partial derivative. So it's like ODE. ODE you only get one direction, but here we got two directions, so we use partial derivative. 会不会熟啊？你们 ODE 有没有算过这样类似的东西啊？看看认得出吗？我指一下给你看。看一下啊，很细。maybe 你看不出，因为我是直接找好给你的，我直接 define 好给你的。But to find this, maybe you need to solve this first. 你们 ODE 有没有做一件事情，就是它 integrate 过后是要找 x， 怎样形容那个 calculation 给你啊？所以你 start with 一个 ODE。And then 你要找它的 solution 嘛，对不对 ？So 怎样找它 solution 啊？你们学过什么 method？ 3个，还是 depend on 你的 order？ 有不是 ？OK， 还有那些 method 长怎样 形容一下。不错啊。OK。啊，说你是有一个 general solution，是不是？有没有一个 solution 是可以从 integration 做出来的？OK，其中一个是那个叫什么 separation variable，但是我不是在指那一个，还有一个啊，哎呀，exact 对 exact，你不觉得很的 exact 吗？我做那边你看的东西，Wait let me show you，我给你看一个东西啊，exact 对 exact，我不知道我之后会不会跟你提到 exact，可能会吧。是啊，你看这个东西的时候，不会觉得有很像 exact 的东西吗？嗯嗯嗯嗯嗯，呀呀，OK，我看一下啊，我看一下，我看有没有好剧透给你，我看一下我会不会讲 exact 的东西。诶呀，let me see。对呀，我觉得我们等一下可能会跟你讲 exact 的东西，到后面的时候，OK，yeah，something related to exact stuff。OK，but anyway，我不要讨论这个 proof，吧，你可以看看怎么 proof。So, but we still have the both direction. Okay, if and only if equivalent definition for this independence of path theorem here. Okay, so we have established three things. So let's summarize here. These three things is the same. Okay, if you have a conservative vector field on an open connected set, it is equivalent to if you integrate this vector field across any path, it should be independent of path. 只有看你的 endpoint 吧。Okay, or if you integrate over closed curve, 你一定拿到零吧。我以为会这样讲。Okay, these three are equivalent。我讲哪一个就会代表另外一个是对的，他们三个是一起的。Okay, make sense? Okay. Okay. Next up, let's talk about simple. The idea of simple，我们不会什么用到吧，就是给你介绍给你听，因为 because some of the theorem need this condition. In future, maybe you will see it again. A simple curve is a curve that does not intersect itself anywhere between its endpoint. Okay. So simple 就是什么？很简单，很 simple，就是你没有跟你自己相遇的相撞。Okay, so first curve is simple, not curve. Okay, because there's no self intersection. Second one, not simple, not close because got self intersection. Okay, and not close because starting point and ending point is different. Third one, simple and close because there's no self intersection. So simple. Close meaning what? The starting point and the end point is the same. Second, not simple but close. Not simple because there is self intersection. Right? Let me ask you a question. If there's a self intersection here, can you do anything to remove this intersection? Is there a way to remove this intersection? Self intersection. 打掉不是变两条线了，then is the not closed curve anymore。一个点啊，怎么？然后分两个区，怎么回事？怎么回事？这样你跟他打掉的意思有差别多？有点差。我不是你在做什么？我不知道你在做什么，你在做什么？你的点放去哪里？我两个白线画出来，把它分开了。哦，你把它 split 掉啊？哦，你把它 split 掉。Okay, let's say I want to keep the closed curve. I want to click a closed curve. 啊？吊起来？什么意思吊起来？你讲清楚一下。什么叫吊起来 ？OK， 那起来，good，这是我要讲的东西。加一个 dimension 上去，上升一个维度，and then we can lift we can split the line。OK， 是不是？你看这里有矛盾吗？上升一个维度了，它就不是个矛盾了，是不是？人要上维度，如果你一直活在低维了，就天天就是有矛盾啊？没有叫你去思维啊，你就上个维度啊 ，OK， 呀，有矛盾，上个维度都不是矛盾来的，要上个维度，这样的，yeah. So if you have 3-dimensional, then you can lift. Maybe you can imagine you lift out the other part of the string. Or how do you think about this self-intersection here? You can think of like what Yi Xiang said. You take one rubber band, right? You can twist it, and then you project down to R2. Then you will have this self-intersection. But if you look at in 3D, you won't intersect. Okay, you won't intersect at this point because their height might be different. Their height is different. 懂什么意思吗 ？Okay, yeah, we can lift up. Yeah. Intersection. Say again. Room. Look. Well, I mean, okay, let me think again. So to put it more precisely is, if you have a path, right? Okay, if you have a path, you can parameterize your curve or your path, okay? And then intersection meaning there's exists 2 times such that these 2 times give you the same point. Okay, so for example, you go from here, and then when you come back to this time, so when you reach this time, we call it T1, and then you reach this point again, you call it T2. So there are 2 time, different time, but meet in the same place. Yeah, what is language? No one. I mean, if I start my 0 here, I can start my point 0 here, and then we actually only need once here. So here is T0, and then here is T, let's say call it Tn. Yeah, close. Close meaning the endpoint and starting point intersect, that's all. So this self-intersection should like occur other than starting point and ending point. Okay. Yeah, so this self-intersection is a non-trivial intersection. Between. I already fixed between. Between endpoint. Endpoint can intersect. Okay. Yeah, must be between. Okay, if it intersect between the endpoint. Anywhere between this terminal point and then we will call that self-intersection. Okay? Okay. 有问题吗？还有问题吗？ Okay. So why we consider a simple curve here? We want to introduce what is called simply connected. So here involve 2 ideas. One is connected, one is simply. So what does it mean? So it has to be connected. First of all, okay, connected means what? Any 2 points you can connect by a path. Where one can continuously string any simple closed curve into a point while remaining in the domain. Okay, so meaning what? For connected, you deal with 2 points. 每2个点 for every 2 points, can you be connected by a path or not? If can, then it's connected. But simple here deal with every closed curve. Okay, every simple closed curve. So every single closed curve, for example, in this example here, we said that it's simply connected. Why? Because if you take any closed curve inside here, you can shrink it into a point. Okay, maybe this process of shrinking is not precise, but let me draw it to you what it means. So when you shrink, right, you should shrink inside your domain. Okay, in your domain. Okay, or you can imagine that this circle here, you can shrink it smaller and smaller into a point. Okay, how should you imagine it? You can imagine it as clay. Okay, maybe 粘土这样吗？clay 哈，clay 哈，okay. So you can mold the clay into one lump 一个点，本来是一圈，对吧？lump 去一个点。Okay. So when can you do that? When can't you do that? Okay. When can't you do that is maybe you have a hole here. Okay. You cannot pass through this hole anymore. Okay. 你就不能把这个粘土变成个点，因为有一个洞的。OK， 这个呢 ，is this simply connected? Why not? 两个洞。So which simple closed curve that you cannot shrink to one point? You need to find right where's the simple closed curve that you cannot shrink to one point. 哪个洞？两个洞的圈，还有一个洞也不能够 shrink。Yes, good, very good. 那你们可以考虑进 algebraic topology 了。yeah， 对，有三个洞，其实这个有三个洞，你 shrink 不到一个点。为什么啊？你看、啊、这最外面那个很神奇耶，它其实可以 shrink。你知道它 shrink 到最小会长怎样吗？要不要猜一猜？这个 curve 如果你 shrink 一 shrink， 它会 shrink 到什么状况？最小啊？什么啊？再小一点不是长这样咯，对不对？还可以再小。3 ，yeah， 一个 dumbbell 这样。OK， yeah. OK， How about this one? Why is it not simply connected? 它不 connected 吧？它其实是 simple 的。Yeah, because if you found any closed loop inside this region, you still can shrink to one point. You still can shrink on one point, but just that you cannot connect any two points. 其实它是 simple but 不 connected. Okay. Yeah, the study of hole is algebraic topology. 那 algebraic topology 我们学洞多少个洞？ Okay. Next. 几点？236. Okay. Okay. Next, we deduce another criteria to check whether a vector field is conservative or not. 所以现在我们讨论了很多 property 都是围绕着 conservative vector field 吧。Okay, so how to check? Again, if your vector field is on an open, simply connected domain, suppose that f1 and f2 has continuous first order partial derivative. Actually, this is most of the case will happen in our course. Then this vector field is conservative if delta of f1 over delta fy is equal to delta f2 over delta of x. Can you notice something weird here? F1 is in what direction? X direction, but we differentiate with respect to the y direction. F2 is in the y direction, but we differentiate with respect to x direction. So we kind of swap. Okay, if they are equal, we will say that the vector field is conservative. Okay. 好像我没有 proof 没有 proof 啊。Okay, we don't need to prove this. So you can extend to 3 spaces. So 3 spaces, you should imagine there are more things to check on because there are 3 directions, right? So there are three more things to check. So what are the permutations here? You still check f1 with respect to fy equals to f2 with respect to x, but you have 2 more things to check here. Okay, there are 2 more things to check here. You need to relate your f1 to f3 and then f2 to f3. Okay, you need to relate f1 to f3 and then relate f2 to f3 here. So not this order, this order is very important. 其实这些东西不用背，反正我给你，应该有给。So you just need to know how to check this. Okay, so let's see how we use this. Let's do it for this example here. Or determine whether this function is conservative or not. So I tell you few ways to check a conservative vector field, right? What are the few ways? 什么方法可以 check 一个 function 是不是 conservative? Line integral, okay, so you can do line integral. So you can check line integral on every part. 我觉得这件事有一点难，因为你要每2个点都要算一次，而且还要算所有的 part. And any more? Line integral on closed curve. OK， 虽然比较简单一点但是还是有一点难，因为你要把所有的 closed curve 都 parameterize 出来。OK， 刚才教了 ，you just need to check the partial derivative. Okay, you just need to check the partial derivative. So in this case here, there are 2 variables, right? So what do you need to check here? So let f equals to f1i and f2 plus f2i. Anyone can remember? It is conservative if what? Del of f1 over del of y equals to del of f2 over del of x. Can you quickly check what's the answer here? Can you quickly check? Can you quickly check? Eh, 你知道为什么会这样吗？我的 good note 啊，它好像会算东西啊，你知道吗？我没有用过。哎，factorize 啊，latex 好像是可以进到 latex，它会打 latex 这样这个本来是用前台，但是之前没有这个功能啊。哪个版本？你买了么？你不是买6吗？变 latex， 从图变 latex， 可以出 latex code 好像。OK， 终于出来了。哎，算完了吗？什么答案 ？check 一下有没有算错。18 x square y。OK， all of you should compute to 18 x square。用眼睛也可以算嘛，对不对 ？By inspection。OK。All right, so they are equal. So this means that f is conservative. 诶，我们有没有说它在什么 domain 啊 ？We need an open simply connected domain。这题目好像没有 domain 呢，你觉得呢？这 domain 在哪里 ？Yes, everything in R2. So R2 is open or not? Open, right? Because every point you can find an open ball around it, and then this open ball should live inside R2. 因为 R2 就是全部啊，所有的 ball 都在里面。然后 simply connected 呢 ？Connected, okay, connected because every 2 point you just form a straight line path 就到了。 对吗？每个点在 R2。What's the path that connect 2 points in R2 啊？You just form the straight line path. How to get this straight line path 啊？就是刚才一想讲哦 ，you take these two vector and then you form the line equation using the direction vector. Okay. And then why is it simple? Why is it simple? Because R2 里面应该是没有动 ，R2 没有动。Every closed curve you can stream into a point. 反正我们这里不太 rigorous 啊，你可以用这些语言，用你想的东西来讲。因为我们也不会让你去检查这种东西 in the course. But still, we need to tell you, still we need to tell you what are the property involved. Connected. So F is conservative. OK， 现在我要让你做一点很 ODE 的事情了。Can you find the potential function or not? Okay, what does it mean by to find a potential function? This means that we want to assume how we get this f. This f should come from a gradient of some small f. Okay, meaning what? The first coordinate should be a partial derivative on f with respect to x, and then partial derivative on f with respect to y. Okay, so basically you just let this equals to your f. So what is your f? That's your vector function here, or vector field. So on one coordinate you have 4x cubed plus 9x squared y squared, comma 6x cubed y plus 6y. Okay. So you want to let these two vector equals. Meaning you got two equations here. Okay, you got two equations here. So what can you play around with these two equations? So let's start with the first one here. Okay. So this says that the first derivative here is equals to this function. So how do you get f? How do you get f? You can integrate with respect to s. Okay, so this is a technique done to say why is it true. So if you integrate with respect to x, what do you get? X to the power 4 plus 3x cubed y squared. Okay. So in the normal calculus, right, you will put a constant here. But here, what should you put? You should put more than a constant. Why? Why? So remember or not, when we do partial derivative with respect to x, we treat y as a constant also. So meaning you need to add the y back, function in y. Okay, you need to add everything in terms of y back to here, not just constant. Because here constant include y variable. And then what do you do? Okay, so you compute, so on one side you have partial f, partial y equals to, let me see here, equals to 6x cubed y plus 6y squared, 6 times y to the power 5. But now you've got a new candidate f prime. So you also can do partial f over partial y on the new f. Okay, so if you do that, what did you get? So on the other hand, partial f over partial y is what? 4x cubed plus 4x cubed. 6x cubed y plus g prime y. Okay, and then you equate these two, partial f over partial y. What did you see? G prime y should be 6 times y to the power 5. So what is g1? y to the power 6 plus a constant. Okay. So this implies that fxy. I don't put the step, you put the step. Okay, write it out yourself. So in total, you should get x to the power 4 plus 3x cubed y squared plus y to the 6, the last one we calculated, and plus an extra constant. We don't know what's the constant. So this constant should be depend on your maybe boundary condition. Okay. Unless I know how to evaluate this function at certain point. Okay. 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 So let's do the last one before we break Friday. Okay. How about this one? Try and compute this integral here. What do you think? What can you do? 来，给我一个方法，我算这个。So this is a SQL question. So this F is the conservative vector field. Okay. But in this case here, the question also tells you the parameterization of your C. Okay, so how do you compute line integral then? Yeah. Sorry? F equals capital F equals to gradient F, meaning what you are using there. Fundamental theorem of line integral. Okay, you can use fundamental theorem of line integral. So if you use fundamental theorem of line integral means what? Means what? Means what? You don't need to use parameterization. Okay, so what you use is use the function that we find from part A. Okay, evaluate at the endpoint. You can find it. Or if you cannot see the problem, there's one brute force or a bit stupid way to do it. You can do the parameterized curve way. Okay, you can go through. You can go through this parameterization and do it. Also can. Both of them should give you the same answer. Okay, so to practice, I didn't say that this is more stupid. You shouldn't do this. You should. Okay, why you should? You should see that these two compute to the same answer. Okay, and then you should appreciate why this is more stupid. Once you know that vector field is a conservative vector field. Okay, you should do the stupid thing. Okay, I want you to appreciate. At the same time, you train yourself. Okay, at the same time, you train yourself. How remind yourself, okay, how to compute. Actually, this is called work done because F dot dr. So how to compute work done through parameterized curve, and then work done through what? Conservative vector field, or the fundamental theorem of line integral. Okay, so these two should compute to the same solution. OK， 有问题吗？你两个都要练一练呢，都要熟一下。OK， 有问题吗 ？Any question? It's more makes sense to use the first way because you already figure out what's the potential function. Then you should use fundamental theorem of line integral. But in case you remember this way, then you should also be able to calculate it. 也要能算得出来。OK 吗？有问题吗？回去 try 啊。Yeah, time up. So please go back and try it. OK。try 完才可以玩 game。OK。开完才可以玩 game， 我妈讲的。我妈讲，功课做完先才可以出去玩呢。OK OK， so see you on Friday. OK，拜拜。